Yeah, good afternoon, everyone. Yeah, I'm Chao from Harvard Institute of Technology, China, and it's my great pleasure to here to present our work on the multi-scale analysis of heterogeneous deformation and damage of welded joints. So just before start, I would like to thank our students and my co-authors. So here is the outline of my talk. And I just like to begin with background and objectives. So in fact, we perform this work because our industry partners found that in their superheater and the reheater in power plants, there are some unexpected failure of the weldments. These weldments are used to join the heat resistant steel tubes. And after careful examination, they found that these failures are due to intergranular cracking. So for us, it's quite challenging to understand both qualitatively and quantitatively this kind of failure because there are many influencing factors, such as the loading condition during surface are quite complex, such as creep and fatigue and their interaction. And also the welding process itself induces some complexity. For example, it checks a large grain size and morphology, and also introduces carpet precipitation and also reduced stress and distortion. And the material itself during surface undergo changes of microstructure and properties, such as the carbide precipitation at grain boundary, which probably lead to the final failure. So the main objective of our work is to review the physical region of this unexpected failure of the weldments, and also to predict the in-surface life of the weldments considering microstructure changes. And so to that purpose, we propose a bottom-up modeling approach to address these three kind of issues. And today I will talk about microstructure related heterogeneous deformation and damage. As to begin with, we conduct some experiments. So we machine such cross-weld specimen from the welded tubes, and we perform tensile tests at different temperatures with DIC measurements. So from the tensile tests, we can extract stress strain curves, not only for this whole specimen, but also for different regions. That is a weld metal region, heat of phase zone region, and base metal region. And also we have the full field strain measurements. We can see that for this specimen after the tensile test, there is a strong strain localization in the middle part. That is a weld metal region. So to model this behavior, we propose such micro-mechanical modeling approach. So firstly, we construct such representative microstructure model according to some careful microstructure characterization. And then we use a crystal plasticity model to describe the elastoplastic behavior of the grains. And then we need to calibrate the models. So we use two kinds of way. One is to do just simple tension of these simplified polycrystal aggregates, and we fit the experiment data that we obtain for each region from the tensile test. And additionally, we do compression micropilot tests to further confirm our parameters calibration. I think we can use this such model to study different behavior of this weldment. So following this approach, we first need to construct such a microstructure model. So we do EBSD measurements to gauge the statistics of the grain size distribution information, as well as a grain orientation distribution. And based on this information, we construct such microstructure model considering grain size distribution using software named Lifeng. And then we use the single crystal plastic model to do simulations. The model that we used is quite classical. I won't go to details of this or into these equations. What I just want to emphasize is that we use the same model for different regions of the specimen, but with different parameter values. So first of all, we need to calibrate such a crystal plastic model. The first thing we do is to run finite element simulation using such a simplified polycrystal aggregates to fit the straight strain curves that we obtain from this tensile test. And as we can see here, there is a good agreement between the experiment and the simulations for two temperatures, room temperature and 600 degree. And however, such way of calibration may raise one question, is that whether these parameters are good enough to describe an individual single crystal. So in order to confirm this parameter calibration, we do micropilot tests for different regions. So the three regions, that is base metal, wear metal, and heat event zone. And we use the parameter that we calibrated with tensile tests data to see whether these parameters are good enough. So as we can see here, there's a good agreement between the simulation and the experiments in terms of the stress strain response, as well as deformation mode of individual micropilot. So with these parameters well calibrated, we go, our first step is to simulate the response of the whole specimen. And as we can see here, so we achieve the goal. That is, there is a good agreement in terms of the stress strain curves for the whole specimen for the two temperatures. And we also calculate this distribution of accumulated plastic strain for two temperatures, and we found there is a strain localization in the middle part, that is the wear metal. And however, this plastic strain distribution is more diffusive at high temperature. That is, of course, because of more viscosity at this high temperature, which are in good agreement with our experiment observation. And also based on the same model, we can do something more. For example, we would like to predict the creep rupture time. And yeah, there is, of course, many ways to do that. We do simply by introducing some indicators. One is cumulative plastic strain, another one is dislocation density based stoichiometry. And we need to use one experiment data to calibrate the critical value of these indicators, and we try to predict the others. So as we can see here, what we have obtained is that there is a good agreement for lower stress levels, but some discrepancy have been observed for higher stress levels, probably because there are some more physics mechanisms that we haven't considered. Another thing that we also have tried to do is to simulate the ductile fracture of this cross-wear specimen under tension. So we use simply a GTN type model for only this middle part, the weld region, and we try to run the simulations, and we see that in terms of these stress drops, we have predict with this model, and we also will predict the evolution of damage parameter in this middle part. So the work is still ongoing, as I have talked about in the introduction. That the creep thing of this movement is quite complex, so we need to enhance the model. For example, we want to consider more deformation mechanism in this single crystal plasticity framework, such as the diffusion-induced deformation. And also we need to incorporate more the failure associated, the mechanisms that induce failure, such as carbide precipitation and green boundary. So this work is still ongoing. So that's my talk, and there are some conclusion remarks. I don't read them, and just thank you for your attention, and